Okay, so in this video again we're working with redox reactions, and since now we know how to assign oxidation numbers, we can now apply them to different reactions and determine which species are being oxidized, which species are being reduced, our oxidation agent, our reduction agent, as well as the total number of electrons being transferred and in which direction those electrons are being transferred. So the first thing to do when working with a redox reaction, as we talked about in the last video, is to assign oxidation numbers. So we're going to start at the left in our reactants and work towards our products over to the right. So always start with the species, the element that you know the oxidation number for. So hydrogen we know is always, or in most cases, a +1. So if our H is a +1 and +1 times 4 is 4, we know each of our carbons must be a -2 to make the overall charge on that molecule neutral. And over here we have 3 oxygens, but it's still an element by itself, only bonded to oxygens, so its oxidation number is 0. Over here on our carbon dioxide, we know that our oxidation number for oxygen is a -2, because again, remember over here our oxidation number on oxygen was 0 because it's oxygen bonded to another oxygen. Over here our oxygen is going to have an oxidation number because it's oxygen bonded to a carbon, so it's bonded to a different element. So -2 times 2 is -4. So for this element to have, for this compound to have an overall neutral charge, my carbon must have a +4 charge. Over here, once again, my oxygen has a -2 oxidation number, and since I have 2 hydrogens, each of the hydrogens must have a +1. So now I'm going to look at how the oxidation numbers have changed between my species and my reactants and my species and my products. And I notice that I'm working with 3 species, carbon, hydrogen, and oxygen. So as I continue on with my reaction and determine which is my oxidizing agent and which is my reducing agent, I'm only going to be working with 2 of the 3 species. So at this point I want to see which one I can eliminate. So carbon goes from a +2 to a +4. So that one definitely changes. So I'm definitely going to be working with carbon. Hydrogen goes from a +1 to a +1. So that doesn't change. So I'm not going to be using hydrogen because hydrogen's neither been oxidized or reduced. And just to be sure, my oxygen goes from 0 to a -2. So the oxidation numbers on carbon and hydrogen definitely changed. So now I'm going to connect my elements that are the same. So I'm going to connect my carbon in my reactants to my carbon in my products. And I'm not going to work with hydrogen because it's neither been oxidized or reduced. And then I'm going to take my oxygen and I'm going to connect my oxygen in my reactants to my oxygen in my products. And it doesn't matter which oxygen in the products I use. I could use either one. So now my carbon has gone from a -2 as its oxidation number to a +4. So since my number has increased, my oxidation number is increased, I know that it has been oxidized. Meaning, if we recall our oil rig, or our Leo says gur, our Leo says gur, there we go. If it's oxidized, it is losing electrons. So it's lost -2 to +4, it's lost 6 electrons. And again, I know to go from a -2 to a +4, I must have gotten rid of negative charges. So I must have lost some electrons. Up here for oxygen, my oxidation number has gone from a 0 to a -2. So my oxidation number has reduced. It's gotten smaller. So my oxygen was reduced. And if it's reduced, it means that it gained electrons, again from our oil rig, or Leo says gur, and it's gained a total of 2 electrons. So from this, I know that my carbon has been oxidized and my oxygen has been reduced. And the direction of electron transfer, if my carbon is losing the electrons and my oxygen is gaining the electrons, then the electrons are moving from carbon to oxygen. Carbon is giving electrons to oxygen, causing oxygen's oxidation number to decrease, to be reduced. Carbon is causing oxygen to be reduced, so it is the reducing agent. Whichever species is being oxidized is the reducing agent, and by accepting those electrons, oxygen is causing carbon's oxidation number to increase. It's causing carbon to be oxidized, so it is the oxidizing agent. Whichever species is being reduced is the oxidizing agent. So now to find the total number of electrons transferred, what we're going to do is we're going to look at the electrons lost and gained. So, and we can look at either one. We can either look at the electrons lost or the electrons gained. For this one, I'm going to start with looking at carbon and the electrons lost. So this lose 6 electrons means that every carbon in this reaction is going to lose 6 electrons. But I actually have, in this reaction, I have 2 total carbons. So 2 times 6 equals 12. So a total of 12 electrons transferred, or lost by all of the electrons, or I'm sorry, all of the carbons in this reaction. So all of the carbons in this reaction altogether lost a total of 12 electrons because each one of the carbons lost 6 electrons. Well, electrons can't just disappear, so the number of electrons lost by carbon better be the number of electrons gained by oxygen. So we look at our oxygen and we notice that each of our oxygens gained 2 electrons, and we have 1, 2 times 2, so we have 4 oxygens here, and 2 times 1, so I have another 2 oxygens over here, so 4, 5, 6 oxygens over here. So 6 oxygens times the 2 electrons gained equals 12. So each of our all of our oxygens together are going to gain a total of 12 electrons. So we're going to have 12 electrons transferred from all of our carbons to all of our oxygens. So each of our carbons is going to lose 6 electrons, and each of our oxygens is going to gain 2 electrons. And that's how we can use our oxidation numbers to figure out our reducing agents, oxidizing agents, by determining which species is reduced, which species is oxidized, and then we can use the oxidation numbers and the total number of atoms of each species in the reaction to determine the total number of electrons transferred.